So now, what's the relevant input for learning this target knowledge that's going to allow us to make those acceptability judgments for different types of WH dependencies? So that depends, of course, on how we think children learn it, what part of the input matters. Okay, so Pearl and Sprouse, us, in 2013, we had this intuition that maybe what the children are doing is learning what they can from the dependencies they actually do observe in the input, and then applying that learned knowledge to make a judgment about dependencies they may not have seen before, like, for example, syntactic islands. Like if we asked them or somehow got them to tell us what they thought about them, they would be able to based on the knowledge that they had acquired from the dependencies they do actually observe in their input. So we came up with a concrete learning strategy, which is simply to view WH dependencies in terms of their building blocks and track those building blocks in the input. So let's talk a little bit about those building blocks. In particular, dependencies are represented or characterized as a sequence of what we called container nodes. So these are phrases that contain the gap right there, but not the WH word, right? So in this case, for this matrix clause dependency, what did you see matrix clause object? It's IP and VP are the phrases that contain the gap, but not the WH word. They are the container nodes, right? And so we can characterize or represent the sequence of container nodes with these two phrases, right? Start, IP, VP, end, right, is how we would characterize this sequence. And you can do this for all kinds of sequences. So here's what a matrix clause subject dependency looks like. It's just the IP node, so start, IP, end, right, for something like what happened. For longer ones, what did she want to do, where you have an embedded non-finite clause. This is IPVP, IPVP. And so again, you have this sequence that start, IPVP, IPVP end, for something like what did she want to do. And so, of course, ungrammatical dependencies can also be characterized this way. This is, for example, this island crossing one. And so who did Lily think the kitty fort was pretty? And, they're going to have the idea as low probability segments in that sequence, and that's going to be like your signal that something has gone awry and you don't like this dependency, right? So if children break these dependencies into smaller building blocks, they can identify if a dependency has a bad segment made up of one or more low probability building blocks. And so the building blocks that we proposed are trigrams of these container nodes. We're going to sort of abbreviate them as syntactic trigrams, but the idea is very simple. You basically take any dependency characterized as a sequence of these container nodes, and you just break it up into units of 3. So here for start, IPVP, end, our matrix clause object dependency, you have start IPVP and IPVP end are the 2 building blocks for it. What you'll notice is if you have a longer dependency, it may in fact use those same building blocks and a couple of others, right? Because you're just breaking it up into these, sequences of 3 units that can be combined together to recreate that original dependency, right? And if you just have a matrix clause subject, start, IP, end, it's sort of the shortest one. It's a unit of 3 that looks just like that. So, of course, our ungrammatical island crossing dependencies can also be broken up this way, right? They use some building blocks we've maybe seen and some bad ones, right? These are our syntactic trigrams. So the strategy then is very simple. You just track the relative frequency of these syntactic trigrams in your input, right? Just how often do syntactic trigrams occur, which ones occur, what's the relative frequency of them, right? Some of them are going to be more common, sort of represented here by size, and some of them are going to be less common, right? But they're just maybe not all that often. And some of them just aren't going to occur at all, right? You're just not going to see them, right? So what you're doing then is just tracking this relative frequency of these building blocks, these syntactic trigrams. We're going to abbreviate that P of T for the probability of that syntactic trigram, and we estimated it in a truly simple way. There are probably lots of different ways to do this, but just the simplest way we could think of is just the number of, say, that trigram over the total number of trigrams you observe is the relative frequency. I made a little teeny bit of smoothing, so if you never saw something, it still has an eensy-weensy bit of probability, right? So these have an eensy-weensy bit of probability if you say never see them, but these ones that you do see, of course, are much more probable. And so any WH dependency can then be constructed from its syntactic trigram building blocks, and all you're doing is just taking the product of those probabilities, right? So here we have start IPVP end, our matrix clause-object dependency made of two very common building blocks, for example. And then we might have a longer dependency made of those more common building blocks, but also, some other building blocks that maybe don't occur as often, but are there in the input. And then we might have our island crossing dependency, right, which has some common building blocks and some less common building blocks, and then some of the building blocks that we just never saw, right? And you're just taking the product of these. Again, there are different ways actually of aggregating this to reconstruct a probability for the entire dependency. We just did the simplest thing, which was just the product of these probabilities. And so a WH dependency's probability, which is what you can construct from these building blocks, can then stand in for its judged acceptability, that target behavior.